Welcome to the fifth lecture on natural language processing and its applications. To summarize what we have learned yesterday, we talked about question analysis, about passage scoring, about textual data preparation, as well as its transformation, and about corpus expansion, that is adding some additional data from the web. And we introduced some basic concepts of information retrieval. Today, we will discuss many aspects of natural language processing in the Watson system. In particular, we're going to talk about search and candidate generation. We're going to review Watson's answering process. We're going to mention Watson in medical applications. But of course, the stuff that we covered so far, that is some elements of machine translation, the use of basic probability calculus in natural language processing, even all the complicated stuff that we needed to introduce to talk about Watson's architecture and Watson's reasoning process, all of that, it doesn't cover the whole field. So we're going to reserve the last hour or so of this lecture to talk about dialogue and discourse, that is going beyond a sentence or beyond an exchange of question and answer. We're going to mention some applications areas that we haven't talked about, but which have a high potential for fruitful use of natural language processing methods. And lastly, we're going to display some links, some resources for those of you who would like to probe further, who would like to understand what's available on the web. So there will be 10 or so entry points. All right, so let's talk about query and candidate generation. Do I have a pointer? All right, so query and candidate generation. We proceed as follows. There is a question that's coming. We perform a question analysis, which involves parsing of the question and extraction of certain components, in particular of the focus and the lexical answer type. We're going to see some examples in a moment. If necessary, we decompose the query into 2 or more queries. And what's happening after that is that we want to generate candidate answers. And we do it using search. And in particular, we use document search, where we essentially send the terms of the query to a search engine, and we try and we retrieve the titles of the documents as candidate answers. We also do passage search, in which we find passages that might contain some or all query terms, and these passages, and then these passages have to be scored, and some information has to be extracted as to whether they contain candidate answers or not. So there are 2 kinds of passage search, and we're gonna cover them both: title in clue passage search and the INDRI passage search and Lucene passage search, which is a different category. but that uses two different search engines. And finally, for some queries, like which actors starred in what movie, we can look up the answer directly in a database such as IMDb, that is in the movie database, or in a database that we created by extracting a lot of so-called prismatic frames or predicate argument type structures from our textual data. So let's see how these processes work, okay? So once these candidates are generated, then of course some other stuff happens, and eventually the candidates are scored and the answer is produced. Right now we're going to focus on this part. So we have three methods of searching, okay? So we search for candidate answers by finding a document that contains the terms of the query and using the title of this document as a possible candidate answer. So if you remember, yesterday we had a query that stated several facts about place, date, and something else about a tournament. And by putting this fact in a search query, we were able to find a title which was US Open, which is a tennis championship held in New York City. The other way of finding a candidate answer was so-called title in clue search. So in this case, the question pertained to a country, and it read that in 1995, if I remember correctly, this person, Aleksander Kwaśniewski became the president of this country. Okay, so the question was which country president was Aleksander Kwaśniewski was the president of which country somewhere in the mid-90s. And of course, in this case, what we look for is we're going to go to Wikipedia, look for Aleksander Kwaśniewski, and then look for titles of articles, so essentially for links to different titles that are mentioned in this particular in this particular article on Aleksander Kwaśniewski. So one of these articles that is mentioned is the article about Poland, and so Poland becomes one of the candidate answers. And then using, for instance, other data such as the article on history of Poland from '89 until present, also in Wikipedia, we can indeed confirm that Aleksander Kwaśniewski was the president of Poland. All right, so that was, these were two searches. One was searching just simply finding the title, and in the other case we were finding other titles based on the terms that exist in the query. After these candidates were generated, some other processes that we're going to discuss later today provide evidence for and against this particular candidate, such as Poland in the article on Aleksander Kwaśniewski. So finally, we need to talk about passage search. And we're going to do it in a moment, but right now, let's just emphasize some other points. So one point is that there is no predefined type ontology. because we have a broad range of answer types in Jeopardy questions, so we can't simply extract all presidents, you know, all Olympiad winners, and you know, all works of art, famous works of art that are created, and that would simply cover, you know, the domain of Jeopardy. This is impossible, and we're going to see some distribution data in a few slides. The second point is that we care about where the candidate's answers come from. So some data, some pieces of text, say Wikipedia, may be more reliable than some other pieces of text. For instance, this stuff that we gather from corpus expansion. So candidate answers carry these kind of metadata about the provenance, because this information is then used to help assess the probability that you know, given candidate is really the best candidate. And if you remember, there is a whole transport layer based on UIMA, the Unstructured Information Management Architecture created by IBM, and which is now the Apache open source project. So this architecture, in particular, this common analysis structure, is used to carry the information from one place to another in the Watson system. So let's look a little bit at a special situation where we have this lucky situation when actually we are looking for something that might be stored in a database. Okay, so in this case, our clue is Robert Redford and Paul Newman starred in this Depression era grifter flick, and the answer is The Sting. So ing here and ing here can be used to make sure that the answer is correct. But what's actually happening is that before we get to the process of checking the answer, we have to generate some candidates. So in this case, we parse the clue with the parser. We find the focus here, which is flick. And this is also the lexical answer type. So the lexical answer type is not a movie, is not one of the predefined types. It's just a flick, and then somehow we have to get from that to a movie. But basically, we are interested in a relationship, okay, actor in, and we have the name of the actor, so we're gonna get this from the named entity recognition, and actor in Redford in something, flick, which is a focus, and we have the same relation for Paul Newman. So both of these, okay, can be found in a database, either in DBpedia, which is sort of a general database of many useful facts, okay, or in IMDb, which is a movie database which contains information about who starred in what movie, what the plot was, when the movie was released, how much money it made, and all the other stuff. So the information is there. And since we have about 6,000 special rules that allow us to go from a parse tree to these special instances, in this case, the easiest way to find a candidate, but it's not the only way, is to actually look it up in the database. So what you see here is a distribution of 20 most frequent relation in a Freebase database, which is a cousin of DBpedia. Okay, and we see that, you know, that stuff related to track, album, artist, film, work written, and so on and so forth. So this kind of stuff that might be useful in finding information about who starred in what movie is actually, it's relatively frequent in these kind of databases. So this is, I mean, we take advantage of it by having the special rules for dealing with, you know, famous actors, movies, books perhaps, and a couple of other situations like that. But that's not going to be the majority of the question. All right, so how do we generate candidates? Well, we essentially take the query, do something with it. You know, we parse, we find certain elements in the query, and then we go after both the structured data, as we saw a moment ago, and after unstructured resources through document search, title include, passage search, and the passage search. And we take advantage of the relationship between the title and the content in title-oriented documents. So that's essentially what allows us to do it. That was a major innovation. People haven't been doing it before. And one of the interesting thing about Watson is that we essentially did it for almost all kinds of questions that passage search is used essentially as a way to augment title-oriented search. And that the data that we get from the web through corpus expansion, as we talked about yesterday, also is partitioned into a collection of title-oriented documents. So that way we know that every document is about something. The same document, especially that stuff that we get from corpus expansion, so the same paragraph might pertain to different titles, and we're gonna store it under different titles with redundancy and so on and so forth. We can afford it because storage is getting cheaper and cheaper. You can buy 1 terabyte hard drive for less than $100 these days. So instead of trying to solve a difficult problem, that is how to paraphrase information in natural language, we take an easier approach. That is, we're just gonna store different versions of the same information, and then depending on how the question is formulated, we're gonna find the best match in one of these paraphrases. It's not always possible, but in many cases we can find close matches, and then we can grade how close this match really is. What else can be said here? Well, we found out that having 2 search engines, especially in the passage search component, is better than having 1 search engine. So we are using the INDRI search engine, which takes advantage of the implicitly developed language model. So we have seen, you know, the language model concept in the first lecture, where we are trying to constrain possible machine translations, okay? And this concept is used throughout computational linguistics, and in this particular case it has been applied to search to provide more meaningful results, okay? So we found out that in general these results that we are getting from the INDRI search engine are better than the ones that we are getting from Lucene. Lucene can be programmed to do anything these days. In particular, yes, you can put a language model there. But when we started, we were using it out of the box only as Boolean search. So we were getting simply maybe not so good results, but they were different. And the advantage of that was that the strategy in Watson is to make sure that we generate the right candidate, okay? If we don't have the right candidates, we cannot score them, okay? And we cannot find the answer. So the diversity, okay, of strategy between INDRI and Lucene gives us a larger collection of candidates that it would be possible just with one search engine. We haven't tried 3 search engines though, and it is, you know, an open question whether, you know, having INDRI, Lucene, say with Boolean search, and maybe Lucene with some other strategy where it would work even better. This turned out to be enough, and it was complicated enough to do. All right, now for structured data, we also have 2 ways of searching. So one is the answer lookup in existing databases, such as DBpedia, IMDb, or Freebase, yes. And in this case, we rely on certain pre-programmed patterns that we can extract from the query, and then we use these patterns as a, you know, as a structured query against these particular databases. And then we have the second database called Prismatic, which contains about 1 billion, we call them frames, essentially predicates with arguments, like say matches take place on stadiums. People drink certain beverages, okay? So, and with the examples of these beverages, so people drink wine, people drink water, people drink coffee. There could be some additional data there, like people drink coffee in the morning, okay? There is no assumption that there is, you know, any consistency there. This is essentially a 1 billion relations that were gathered from a large corpus and then filtered by a collection of statistics to essentially get some typical instances of predicates and arguments. And this is used both to check answers and to generate answers if we can find clearly sort of a predicate argument relation in the clue. All right, so we discussed document search, we discussed title in clue passage search, more about it yesterday. We discussed the passage search where we don't have any titles in clue, we just go to textual sources, and we discussed 2 ways of looking up for the answer. So how is it all put together? So we're gonna now essentially review all these steps sequentially, starting with the query and ending up with the answer. So let's do it, but before we do it, we're gonna provide a little bit more context. So what it is that we are actually doing, how do we differ from a search engine? How do we compare a search engine versus a question answering system, yes? So if you use a search engine, you start with a question, you type a couple of keywords, okay? You're gonna get documents containing keywords, and based on essentially popularity, we're gonna get snippets and then, you know, the documents with answers. Some of them will be good, some of them will be bad. Very often, as we have seen yesterday from these example queries that were present in the AOL collection of web queries, this process is iterative, where people add additional information to the initial 2-3 keywords. They revise it. All of that, you know, takes some time, but often, but not always, you can get quite a bit of useful information. In question answering, we want to make this process simpler. So essentially, the question is asked, all right, and it would be, you know, easy to ask by speaking. Yes, that's essentially where we would like to go. Just be able to ask the machine a question and get an answer, and then the expertise is encoded, okay? So it's the role of the computer expert to understand the intent behind the question, produce many possible answers and evidence for them, but not necessarily show them to the user, okay? There is no arrow going here. And then analyze this evidence, and then finally deliver response, evidence, and confidence to the user, all right? So this complicated process is hidden. So here the user was, the decision maker was responsible for doing a lot of complicated stuff. Here this is hidden, and we have shown that with enough machinery, even in a very large domain, we can do it fast. That is, you know, within a second or so. Now, I said broad domain, okay? And here is one measure of why sort of the Jeopardy domain can be called a broad domain. We have a distribution here of different, of what it is that the clue is looking for on a random sample of 20,000 questions, okay? So we have 20,000 questions. It turns out that we have about 2,500 distinct types, but we have a sort of long tail situation where, I mean, we cannot just say that we're gonna only, you know, encode the first 100 types, yes, and have, you know, we have, say, for 50 distinct type and relations, we have about the 6,000 prologue clauses that we mentioned before. If we were to do it for 2,500, we would need sort of a huge amount of special purpose machines that would just take care of, you know, of these 2,500 types, and that doesn't exclude other types that might appear in other questions. So we have that the most frequent occurs only about 2.5%, and it has a very, very long tail. So since any of these can be asked, the strategy of simply creating sort of a special purpose machinery to answer a question, say about a song, about, you know, about a fruit, about a color, okay, is not gonna work. For some of them, yes, it's worth doing because it can be done with a high precision, and then there are specialized databases that we can take advantage of, such as IMDb or DBpedia. For others, it just doesn't make sense. So that's why we have, you know, this strategy of finding a possible candidate answer from the search, finding many of them, and then decide, and then having many different algorithms that decide how good these candidates are. So we do not attempt to anticipate all these questions. We do not try to build new databases. We do it to some extent, but the bulk of the work has to do with finding answers through search, finding many such candidates, and scoring them properly. And as we mentioned before, we are not trying to build a perfect logical model either of the language or of the world. Instead, each question will be matched with the answer and the evidence, and partial matches will be scored, and a collection of scores will be weighed, and then after all this numerical data is gathered, a final score and the confidence will be produced together with the answer. Well, it says here that our focus is on the reusable NLP technology for analyzing vast volumes of text, and structured sources provide background knowledge for interpreting the text. So this is obvious, but I just want to say that we do have some experience in reusing these methods. That is, I'm going to say a few words about the use of the Watson technology in medical domain, which we just started working on, but it does look somewhat promising. It's a much more difficult problem than Jeopardy. Nevertheless, I think we will make some progress there. We also looked at applying this technology in call center situation where somebody needs technical help. There, I think it's too early to tell how well it's going to perform. The initial tests that we have done show that it does perform better than, say, regular search. But putting it in practice, of course, is a complicated problem, not only technically, but also organizationally. All right, so if we have the question, when 60 Minutes premiered, this man was a US president, okay? So what happens, all right? We have a question, we have a clue, and in this case, obviously, we will not find any predicate that could be directly matched because essentially what is required is that you are supposed to figure out when this show appeared first on American TV, and then, from this period or a year, figure out who was the US president, okay? This is not going to be something that you can find in a database. A database might say that, Kennedy was the president from 1960 to 1963, but it will not have anything about, 60 Minutes or any other TV program exactly at the same time. So we need to decompose this question and find out information about the show, find a number of candidates who might be presidents, okay? So now, what do we have? If we simply do this question first, we can find information that, the show premiered in 1968. So either we already have a list of presidents, or we can now change the original clue into this clue, and now we have a simpler question, which is, in 1968, this man was a US president. This could be looked up, this could be found through text search. So there are different possibilities, but the point is that the architecture allows us to decompose the question and then apply different algorithms to different ways to decomposing the question and different ways to answering each of the sub-questions. So we've seen this category, common bonds, before when we talked about language models and n-grams. So in this clue, we want to find what it is that's common to shirts, TV remote controls, and telephones. So the answer is buttons, yes, and this is again done by some kind of a spreading activation method using the language model as guidance, for instance. So if we have this collection of n-grams, we can find n-grams with shirts, with TV remotes, and telephones. We can intersect them and see that, and in this intersection, among other things, we're gonna have buttons. A more complicated question would be like the one here below, okay? On hearing of the discovery of George Mallory's body, he told reporters he still thinks he was first. I mean, we talked about finding reference. It is not even clear if he refers to George Mallory or if he refers to some other he, or if this he, or if there is only one person, yes? So the machine has to understand that because of the grammatical relation, this particular he should not refer to George Mallory, which is a non-trivial thing to do, that we are looking for a male person, and there is some relationship of being first, but it's very vague. So how do we go about solving this problem? Well, I mean, we can find information on George Mallory, and what we're gonna find out is that George Mallory is sort of very strongly associated with Mount Everest. So now we have Mount Everest and being first, okay? So he was first and on Mount Everest, yes? That would be essentially the intent for the question, he was first with Mount Everest supplied by this part of the clue. So that is relatively easy to answer, at least to generate the candidate answer, which is Edmund Hillary. And then checking that indeed, there are many sources that confirm that Edmund Hillary was first on Mount Everest. There are some questions, some clues which require decomposition and synthesis, okay? Edible rhyme time, okay, this is a category that appears quite often, so we had to actually program special mechanism to just deal with certain types of clue. I mean, Watson does not have general intelligence, all right? So for many of these puzzle questions, we needed to have a special mechanism that would allow us to answer these questions. On the other hand, the special mechanism used the parts that were developed for answering Jeopardy questions in general, all right? So in this case, we can take advantage of the mechanism that was developed to answer questions about definitions. So we are looking for a name for a long, tiresome speech, and we are looking for something which would be a pie topping, yes? So we can try finding these in dictionary. So in particular, we can find whipped cream. This we can find as diatribe. Yes, but okay, diatribe and whipped cream do not rhyme, and we have here the category is edible rhyme time. Okay, so it has to be something the words have to rhyme. So synonym search produces harangue and meringue, and we can synthesize the answer in which, this would be the answer, meringue, harangue. Okay, the reason harangue is at at the end is that that we follow sort of the natural language order of head noun being at the end. So this is a modifier. This is the head of the noun phrase, and this is also a head of the noun phrase, and this is the modifier of the noun phrase. So the knowledge of language allows us to create the answer in the correct, put the words in the correct order. All right, you've seen this chart before, but let's just go through it once more. When we started, the performance curves looked like this, more or less. So if we decided to answer 50% of the question, only 15% of the questions were correct. If we decided to answer 90% of the question, well, only 12% were correct, and that wasn't winning performance, because to win, you have to be more or less in this space, which means that you have to be able to answer 60% of the question and be, have almost perfect performance. You cannot make, more than one error among the questions that you answer. And keep in mind that this 60% does not mean that you have to know answers to 60% of the questions. You have to be able not only to know the answers, but find them fast enough that you can buzz before somebody else who knows the answer does it for you. Yes, so if so this is, you have to win the buzzer. Not only you have to know 60% of answers, but you also have to win the buzzer. So in practice, you need to be, your knowledge has to be somewhere in this space, and in terms of of attempts, and then nearly all your answers have to be correct. Jeopardy penalizes for incorrect answers. We've seen this chart before. So we saw strategies for generating answers through search. We saw also in another lectures various strategies for answer scoring and deciding what evidence we see. So we're gonna review some of it right now. So starting with the question, which is in 1894, C.W. Post created his warm cereal drink Postum in this Michigan city. So we are interested in finding a Michigan city. We find this lexical answer type and the focus of the question from the natural language parse. So question analysis gives us this thing. This is what we're going to be looking for. And now we need to find a city which is in Michigan, or at least that is modified by Michigan. and we need to connect it to some warm cereal drink and to the year 1894 and to a person CW post. All right, so what happens next? Okay, so this is not really readable, but that essentially repeats the clue. So this is so CW Post created his warm cereal drink in this Michigan city. What do we get out of that is, well, we get some keywords. We have the lexical answer type with Michigan City. We have a date, which should be 1894. This is mistyped here. And we have relations, create, post, cereal, drink. We do search, that we discussed a moment ago, and we generate candidates. So the candidates, which are titles of the documents, could be general foods. I don't know why we have 1985. We have Post Foods, we have Battle Creek, we have Grand Rapids. Okay, so these are many candidates. Usually we get 100 to 200 of those. And then we're going to be checking these candidates. So we're going to, find evidence for each of these candidates. And the types of evidence in this case that we're going to be looking at are lexical, okay, taxonomic, spatial, so this is where we want to know whether something is in Michigan, and then temporal, where do we have a connection to the date, yes? And then lexical, is it a city, okay, or is it a Michigan city? Is it some, is it a city in some database? So what are our top candidates after accumulating, these numbers that come from different dimensions of evidence? We have Battle Creek, we have Post Food, we have 1985. Okay, so again, to describe how we're getting the lexical answer type, well, we have a parse which essentially establishes the relations between different entities in this clue. So in the middle here we have the drink postum, and then the drink is related to CW post through the relationship noun modification. Okay, and also we have a relationship postulated actor of, because we have the word created, okay? So in particular, that would mean that we will also attempt to answer these questions by going to a movie database. It would be unlikely we're gonna find anything there, but the machine doesn't know the meaning of the word created, okay? Language is ambiguous. And then we have, the information about the date related to the word created. We have warm and cereal related to drink. And then we have this city this Michigan city goes into in city, which is in Michigan location. All right, so this is essentially what we get. This is the structure that we're gonna get from the parse tree, and then we have a bunch of keywords that can be used to create a search query. So what do we get from the search? Okay, so from the search we get a collection of documents. So from the title search we're gonna get general foods, Battle Creek, Post Foods, Will Keith Kellogg, breakfast cereal, John Harvey Kellogg, CW Post, Kellogg Company, Postum, yes? In the passage search, we have a collection of passages that mention some of the entities that appear in the clue. We need somehow to, we have to find which of these might be relevant, and then we need to see how would any of these passages reinforce evidence that the answer is, say, General Food versus Battle Creek versus Postum, okay? And and would they include, for instance, breakfast cereal as the answer? So let's assume that we simply have these 4 candidates: General Foods, Battle Creek, Post Food, and Will Keith Kellogg, yes? So now, we can try to combine certain types of evidence. So in particular, we have document rank, okay, so how high in the search results did we get General Foods? Okay, that was our first item. Then we have passage rank. Okay, where does the General Foods appear in the second passage? Okay. And then we have Post Foods. Okay, appears as the third document with number 1, and as a second passage. Battle Creek appears as the second document and in the third passage. Okay, so this is part of the evidence that we're going to be using. But we are not done yet, because we know that we are looking for a city. So now we apply other answer scorers. So we apply type coercion, so we're going to try to see if any of these could be understood in the meaning of city or Michigan City, okay? So could General Food be a city? Could Post Food be a city? Could Battle Creek be a city? Could Kellogg be a city? And, could Grand Rapids be a city? So from that, we have that that Battle Creek indeed is a city, and Grand Rapids is also a city with a higher score. We have more evidence for Grand Rapids to be a city than for Battle Creek. So this comes from looking at text. We also have a gazetteer, which is essentially information about, where different places are located. And again, from there, we can confirm that Battle Creek is a city, and not as the same for Grand Rapids, and none of the other ones are. So in a sense, we are left with, we're going to be left with Battle Creek and Grand Rapids, but there could be some other passages and other scorers that, that believe that General Foods and Post Foods are good answers. So the evidence comes from, from many such passages, and there are many scorers, more than the ones we've shown before. Nevertheless, once this collection of evidence is gathered and put together, we're gonna have that that among the first 3 candidates that that we have Battle Creek with these numbers 0.8 and 1 from evidence features, and we have the previous scores, the ranking scores, yes, which were somewhat different, and then we had some other candidates, candidate generation modules, perhaps from passages, would generate some some other list. All right, so we have, so all these candidates are put together, and we have a collection of candidates going this way and collection of features going this way. We use probably about 400 features altogether. Not all of them on all candidates. Some of them don't make sense. So puzzles are, for instance, scored differently, but there is a few hundred features. And essentially what happens next is that, all these features are weighed by a logistic regression function. So essentially we create a big sum, a weighted sum of these features, and then we do a smoothing to provide sort of a range of confidence values between 0 and 1. So finally, okay, we get that Battle Creek wins in this competition among candidate answers and gets relatively high score, but we can't exclude some of the other candidates. We only get so the best answer with high probability. All right, to finish this segment on Watson, okay, so this is the team that started the project. I am not there. I joined a year or half a year later, so there was about 12 people. When we finished, we were between 25 and 30 people. I am standing here, all right? And what I want to cover now is a little bit about the development process, okay? So some of it was discussed yesterday when we were talking about corpus preparation. But essentially, the procedure consisted of starting with a current version and then identifying errors that the machine is still making, deciding if these errors require a solution that is algorithmic or whether perhaps new sources should be acquired. Then what really, if we were to solve these problems identified here, how much improvements can we expect, and how would we go about solving these problems? Do we have to solve, the general problem in language understanding, or can we simply add a new function or create a new dictionary? All right. Once we decide what to do, say acquire a new resource, then we get the resource, we implement, we evaluate, and sometimes it works, sometimes it doesn't. If it works, then we put it in the system, and that becomes sort of the new baseline version. All right? So that was very much an iterative process. Every step in that process was documented. Every trial was documented in the experiments, and altogether we ran over 9,000 experiments before the game. The tools that we were using, and some of them you're going to see in the next slide, is we had a data repository where we were keeping the question sets. The tests questions were under a lock because we were trying to separate the development from tests. We were keeping indices, so the indexed collection of text, various language models, annotated data, all of that was in a data repository. We had a job scheduling and management tool because the system required quite a few of resources, and people would try to run experiments in parallel, so some procedures for allocating resources were necessary. We had an error analysis tool, which you're going to see in a moment, and we also saw it yesterday, where you could browse the results of an experiment and compare differences that happened, the differences between the results of some experiments. And then you could drill down on particular features. So for instance, you could see what the algorithm did to a particular collection of passages. All right, so that's a screen showing the error analysis tool, which essentially has the experiment number here, some description of the experiment, and if you click on it, you can see some particular results. You can compare multiple experiments as it's happening here. So you have experiment number 8594 compared to experiment number 8608, and we have 3,571 questions. We have the accuracy of the first experiment at 64 more or less, and here the accuracy of the second experiment at 54. So obviously you can ask a question: what happened? Why did the accuracy drop? What was changed? And what it is that can be done about it. You can look at particular clues. Okay, so here we have a clue which the machine doesn't answer correctly. The correct answer is at number 2 in both cases, in the first and the second experiment, but we see that the confidence factors for this answer change. So in this experiment, the machine is less confident that adultery is the correct answer to this question about crime. And so this is a welcome change, yes? I'm sorry, no, this is a wrong change, because this is the later experiment. So here it's more confident. So the confidence increased for the wrong answer, and here we have that the confidence decreased for the correct answer. Why exactly it happened, we would have to look at specific scores given by different modules. So given this methodology, essentially what was happening is that we were improving the systems. So that was the original system that was in 2006. That was the first system that used titles as answers and had the whole Wikipedia as a collection of data. So obviously that wasn't enough to win the game. It wasn't even close, yes? But then with the acquisition of various new sources, with algorithmic improvements, we managed to make relatively fast progress, from here to here, and then the progress became more and more difficult. So as you see at the end, these lines are very, very close together, and somewhere around the time when the system was frozen, yeah, we were definitely, in the winner cloud, but at the game, we had no certainty that, that the machine would win, okay? I mean, it was a surprise to us. It was a surprise to many other people that that the machine could win against some very very good people, the champions of the game. All right, so I want to finish this part of the lecture by essentially showing this final Jeopardy video, and I hope this can be heard. and then we're gonna have a 10-minute break. I don't know, is it the read? I mean, can you see or? Right, so let's talk first about what's on after the game. The focus of the group changed from answering Jeopardy questions to try to apply the same technology to medical diagnosis. So this involves a couple of things. First of all, finding appropriate resources, finding medical questions, finding, I'm sorry, I'm gonna start all over, okay? So let's start all over. So after the game, the focus of the group changed to work on medical diagnosis, to apply the question answering in medicine, all right? So this involves several things. First of all, the domain is different, okay? So we will have to focus on a different set of concepts and relations, and we would have to understand how questions are related to the process of diagnosis, for instance, or in general to a clinical process workflow. It is not obvious how to fit a question answering system into a general system for, for dealing with clinical information and decision supports there. And finally, we need some scenarios. So some of the scenarios that we consider have to do with helping the nurses administer the regimen of various drugs. So checking for drug-drug interactions, checking for possible side effects of drugs given patient condition, and so on and so forth. The other aspect or the other scenario that we want to deal with is diagnosing diseases. The reason for that is twofold. One is that that would be very similar in some sense to answering questions in Jeopardy, because instead of having a certain collection of pieces of data about an entity, in this case we would have a collection of symptoms, and based on these symptoms we could perhaps diagnose disease. Another reason for focusing on medical diagnostic questions is that there are resources that look very similar to the resources that we had in Jeopardy, although the numbers are smaller, which pertain to testing students in diagnosis. So there is something which is called doctor's dilemma, where a student is given a combination of various symptoms, and based on these symptoms, he or she is supposed to diagnose a disease. So such questions exist, and this allows us to attempt relatively quick domain adaptation. Of course, we need medical texts, some medical encyclopedias, perhaps some journals, and we acquired some of these resources. Even the Wikipedia, when restricted to medical concepts, it proved useful in answering questions, but it is not nearly as useful as it was for answering Jeopardy questions. As we discussed yesterday, any content that is created for human consumption, say to be printed or shown on the web, cannot be directly used by the machine. What we need to do, we need to adapt this content. Very often it requires dividing it into smaller documents, but in all cases what we want to do is to create a collection of title-oriented documents, because we want to use the same strategy of generating candidate answers through search and some other means, and then comparing different candidates on different dimensions and generating a final score that way. We need ontological information, which essentially provides us with different ways of naming the same disease. Okay, the same disease can have different names. Okay, the attributes can be used different ways. So you can have lung obstruction, you can have pulmonary obstruction. With more modifiers, they can be put in all different places. Latin words can be used, and then some of them, are related. So, for instance, influenza can be treated as an infection. Okay, so we need to know how to relate, particular disease to a class of diseases. So we use for that as a basic ontology, we use something which is called UMLS, which is an ontology provided by the National Institute of Health in Washington, D.C. And then the final aspect is that, we have the same pipeline, but and we would like to generate candidates in a similar way, but what we need to do is we need to adjust the features, okay, the features that would allow us to properly weigh the candidates, and the candidate scoring must proceed differently because, say, the value of different sources will be different. So the system has to be retrained. And in particular, we have to find the new weights for this final logistic regression of putting the scores through logistic regression. I mentioned a moment ago that we have this collection of doctor's dilemma questions. So they are Jeopardy-style questions in the sense that you are supposed to provide a short answer based on a collection of pieces of information. This is a competition, okay, so they are using in a similar situation. So medical students and residents can take part in it. And what we wanted to test was essentially whether, the same strategy that we use for Jeopardy could be applied to diagnose, a tricky medical situation. So here we have a question: the syndrome characterized by narrowing of the extrahepatic bile duct from mechanical compression by gallstone impacted in the cystic duct. All right. So it's more complicated language. It's not obviously clear what it exactly means. But it has certain syntax. It can be parsed. We can find, again, the lexical answer type. So we are looking for a syndrome here. And then we have, these various pieces of information that can be used by a search engine to generate a possible candidate. All right, here we have a shorter clue where we are looking for a gene, okay? And again, I mean, the same strategy could be used, but what we found is that there is a much more diversity in the medical language than it was sort of in the Jeopardy language, which requires us to find more resources and to be smarter about, matching the same description or the same symptom which would be generated, using completely different words. So, for instance, somebody can say high fever. Another doctor for the same condition can say the fever of 101 Fahrenheit. Yes, there is really no syntactic match. You have to know that the high fever condition can match 101 degrees Fahrenheit. Well, we have more questions like this. Yes, so. So altogether, we got about 5,000 questions for this experiment. We had to clean them, okay, because they were not created for the machine consumption. So some of it, we have to decide, where the answer is, put it in a format that's acceptable to our system, and then we used about 1,300 questions to train, to decide, how much evidence do we want to provide to one medical dictionary versus the other, what it would be the value, say, of Wikipedia restricted to medical questions when it comes to sources, and then we had to decide which of the algorithms should have more value. Is it more important to find, the same predicate argument structure, or is it more important to find the repetition of similar words? Okay, so all of that was done using about 1,300 questions. And then we ran the same kind of collection of experiments trying to improve the system, and then eventually tested on unseen questions. All right, so what you see in these graphs is that, yes, after the training, we can improve the performance. So the system is modifiable, and it matters, what are the coefficients for various pieces that score the results. We get about 70% of correct answers among the top 10. The good news is that, that in medicine, when performing diagnosis, is not enough. It's not necessary to provide only one answer. Yes, if we can provide, say, 5 answers and make sure that the doctor considers all these possibilities, I think we have achieved our goal here. So you see that the system is not perfect, but with more data and better algorithm, we believe we can make it work really well in the domain of diagnosis. Okay, so what you see here is essentially a simulation of a situation where new type of information is added, and as the new information is added, the evidences for and against certain conditions change. So these bars sort of fluctuate depending on, when we add family history, patient history, medication test findings, and eventually, after all the data is added, this looks like the most probable diagnosis, but you see where the weight is coming from. Most of the weight is coming from the symptoms and from the tests. In other cases, family history might have more weight. So the idea is, again, that we not only provide the answer, but we provide the profile of the evidence for the answer, and the doctor can, dispute this evidence, and in principle could weigh some other factors more strongly. So where do we see Watson being applied? Oh, okay, so we mentioned healthcare, life sciences. Okay, so diagnostic assistance, which you saw just a moment ago. Evidence-based medicine. So that would be, making sure that the therapy that is proposed actually has some support in medical literature, and Watson, at least in principle, is capable of checking that. We run some experiments with help desks. So this could potentially be a large application of Watson or Watson-like technologies. Knowledge management in the enterprise. I'm going to mention a few things in one of the last slides. I mean, I worked in this space for a number of years, mostly dealing with semantic search. And then government information, providing information to citizens, but also, of course, in some security-based national intelligence kind of applications. There has been a lot of discussion in the press about what Watson can or can't do, mostly in the form, that Watson can do something, like could IBM Watson lead to disruptive innovation in US healthcare? Can Watson IBM supercomputer cure cancer? Okay, so we have, the progression of superlatives. On some level, it's nice. But creating a disruptive innovation in US healthcare, it's not going to be easy even for Watson. Okay, and here we have, will supercomputer Watson be a superhero for banking? So there is still quite a bit of press interest. This is just from a few days ago about a possible application of Watson in finance, okay, and the idea here is quite simple. There is a lot of data there. People have no time to sift through these mountains of data. So if you provide a question answering system, then perhaps the analyst will perform their work more efficiently. So we are talking about the really large amounts of data. Okay, so here 600 petabytes of data was mentioned. Our original Watson corpus was on the order of a few hundred gigabytes, together with replication and with semantic information extracted from the text itself. Okay, altogether the machine could have something like the 2 terabytes of data, yes, and here we are talking about 600 petabytes. With enough parallelism, it's of course possible, but it is not clear that that more data means better performance. So we'll see how this thing develops. Now, there is more stuff in language processing than Watson. Okay, Watson is an important step forward. Okay, we showed for the first time open domain question answering. So there are reasons to celebrate, but then there are many other aspects of language processing which are very much open problems or open spaces. Okay, so in particular, dialogue and discourse processing is both. We are building applications that perform dialogue. We analyze various pieces of discourse, especially of spoken discourse, but we do not have sort of a general purpose dialogue engine that would be capable of a natural conversation with a human, even in sort of a large domain. I mean, we can simulate relatively natural conversations, say, when it comes to airline reservation or banking or providing some government information. but we do not have a general purpose engine such as Watson that would be capable of doing dialogue. The second domain is reasoning and language processing. Okay, here this story is as follows. Okay, you can believe by looking at Watson, okay, and sort of not going into the details of how it works, that you know, the reasoning problem has been solved. However, it is not so. We still do not know how, given a collection of textual data, reliably perform certain inferences. So, for instance, answer a question whether, you know, this particular fact follows from a particular collection of data. Watson does it to some extent for, you know, for certain simpler types of facts, but the general problem is completely open, partly perhaps because we really don't have a good representation of meaning. And finally, the application of text processing technologies is only now entering the mainstream. So I think for the next 10 to maybe 20 years, we're gonna see a lot of interesting development, and there is plenty of stuff to do, and I will show a few examples in a moment. At the end, the last slide will give you some pointers if you would like to explore these topics further. So let's talk a little bit about dialogue, which is sometimes spelled with a G at the end and sometimes with a GUE, and about conversational agents. So what makes it different from, you know, from question answering as in Jeopardy is that there are turns. In Jeopardy, essentially, we had, you know, one turn, one question, and then you provide the answer. In a real dialogue, you know, people take many turns. They make choices from many possibilities. We often don't know which way the conversation is gonna go. This helps with a very effective transfer of information between people, and we have nothing like that that would allow us, you know, to say to learn by querying a computer about, you know, about a certain domain, essentially using a computer as a tutor. I mean, we do not have such systems. Another thing that dialogue allows is a quick coordination of action, and there are some speculation that's essentially how spoken dialogue evolved. That's how speech was developed in humans. We can observe that dialogues are possible because of grounding, okay? People must share the same underlying assumptions. They have to be anchored more or less to the same reality for the dialogue to be possible, because the expressions have to refer to something. But a more interesting fact is also that often, actually in almost any dialogue, we see assumptions and conclusions that are unstated, but they are used in subsequent turns. We call it conversational implicatures, and we're going to see a few examples in a moment. And finally, another thing that we should know about dialogue is that there are some rules that a good dialogue should follow. So these rules are very difficult for computer to adhere to, because they really require some semantic knowledge which computers typically do not possess. So on this slide you see a user-computer dialogue with a chatbot called Eliza. You have seen this example before, and this is a relatively natural sounding dialogue until you would see what happens next. That is, you know, I mean, the point is that this pattern of answers, yes, I am sorry to hear something, and if something is negative, then, you know, then the computer will always be sorry to hear about it. If the computer sees the word always or all of them or something like that, it will always ask for a specific example. Of course, there is no understanding here, but the computer can pretend to understand to encourage the user to continue the dialogue. So at turn taking, okay, especially among multiple people, there is typically we know who's gonna speak next, okay, or if, you know, or anybody can speak, or, you know, the current speaker can continue. This is usually understood by humans relatively well, and we have some rules about, you know, when for interrupting. So at school it would be, I don't know, raising your hand or something like that, and providing some visual clues in some other conversations. Even silences have meanings, yes? So you can have this dialogue, is there something bothering you or not? There could be a pause, and, you know, you can repeat the question, yes or no, and, you know, somebody doesn't answer, you can repeat the question again in a different form and get an answer which is not necessarily truthful, yes? So human dialogues are very rich. This kind of richness is very difficult to replicate. On the other hand, I mean, it's relatively easy to ground dialogue when, you know, when the domain is, for instance, airline travel, yes? So you can have something about returning on flight 1118, and then, you know, continue with, I will take the 5 p.m. flight on the 11th, and then, you know, acknowledgement on the 11th. Basically, there is a context of the conversation here that does not change, okay? And that makes the building of conversational machines that perform these conversations in relatively restricted domains possible. Now, this would be more difficult for a machine to understand, okay? If the question is, when do you want to travel? And the answer is, I have a meeting in the early morning on the 13th, yes? It has to be deduced, yes, that this is somehow related to traveling and to a specific place. So for humans, this kind of information is very easy to be derived. For the machine, it isn't. So I don't know of any system, I think, that would be capable of actually getting this conversational implicature and, for instance, asking, you know, do you want a flight on the 12th, given that the meeting is in the morning on the 13th. The so-called Gricean maxims or Grice maxims deal with what makes a dialogue successful, what makes a conversation successful. And basically, there are certain rules which good dialogues adhere to. So for instance, make your contribution informative. but do not provide too much information. So the balance between these two is something that is difficult to maintain, even for humans, yes? You are not supposed to take to talk untruth, yes? And you should not talk about things for which you do not have evidence unless you specifically say so, yes? So falsity or, you know, a speculation should be marked. Typically there is a topic of conversation, so you want to adhere to the topic. And then how you speak, so you should, you know, your syntax shouldn't be too ambiguous, and similarly it shouldn't allow too many semantic interpretation. Don't use the words that somebody else won't be able to understand. Don't talk too much, and try to speak in order. So that's essentially, you know, this is a collection of maxims that a good dialogue would satisfy. If you remember from yesterday, we looked at some of the robot conversations, okay? So we have this conversation between a human and a robot, okay? So the robot is here in the bold face. And if we read it, okay, we see some, you know, some strange things happening, yes? I'm pretty tired of this weather, so I guess the robot is getting tired, but maybe doesn't understand, you know, the causal relation between the tired and weather. So it's what are you taking for that, which almost suggests taking like medicine, but okay, we can let it pass, yes? So we have the answer, lots of coffee, and then we have this continuation, I have coffee in my garden. I mean, this really, you know, this is a change of the topic, which is not licensed by anything that happened before. So the judge in this competition, the human, asks coffee beans or just coffee, and again, this doesn't provide the answer. So this violates some of the Gricean maxims. This again would be a violation of a Gricean maxim. So you can, I mean, you can go through this dialogue and see which of the maxims are violated at various turns, and I guess that may be one way how people can distinguish, you know, the human from a robot in this Turing competition, in this Lebner competition that took place, that was in 2010, but it takes place, I think, every year or every other year. So what it is that can be done in the dialogue management? So natural dialogues are not possible, but we can have, you know, a dialogue system that, for instance, takes a reservation, an airline reservation, and more recently, Apple introduced Siri, a personal assistant, which can respond to certain commands which are spoken to a cell phone. This can be viewed as the extension of this classical model which we're going to talk about. It has only a finite number of domains, so it's not completely open-ended, and it's very much task-oriented, so it's very much you know, similar to something like airline reservation. So in the late 90s, I worked in a group that created leading dialogue systems, and essentially they all shared the same properties. They were task-oriented, the domain was small, we allowed free-form natural language conversation, but it had to be focused on the tasks. So we had a parser from which we could extract the structure of the conversation, And then because the domain was small and the task was limited, we were able to map it into some kind of a logical form, and then from that mapping generate the next turn in the dialogue. There was a goal, which was basically accomplish the task, and the task could be like provide the information. So what is the current interest rate on the bank CD, or what is, the best laptop for a university student? This would be the kind of information dialogues. Or it could be a transaction, so transferring money from one account to another, or transferring the call to a particular department in the office. This was well received also in academic community, because it was, we believe, the first free-form natural language dialogue engine built. And then it was used commercially for a number of years. Turned out to be quite reliable. There were versions that used spoken language, and there were versions that used a dialogue on the web. What these engines shared was an architecture. So you had a user, the user interacted through some kind of a presentation manager. So this would be a window on the web. It could be sort of a voice input and output for the phone conversations. And then what would happen is that there were modules, natural language parsing that dealt with, it should be NL parsing, natural language parsing that dealt with understanding the user, and then some generator from the template that would try to generate the next sentence spoken by the system. The dialogue manager took care of deciding what it is to ask about next, and to see which of the parameters of the actions are given and which ones are missing. And there was some connection to a background system, so product catalog, a document collection, or HTML page, or a bank account API, where this action manager could either provide information, or it could perform a banking transaction through the API, or a transfer transaction as through the telephony API. The manager was declarative, okay? So there was a collection of rules which specified that in certain situation, certain actions, certain actions should be taken, which meant basically that the next sentence should be spoken. So how did they look like? All right, so we had, an XML entry that looked like this, that dealt with affordable concepts. So this was the semantic level. If we wanted to ask about affordability, we would use a question like, what are your financial constraints? Or we could, for variety, we would have a question, is affordable price important to you? So we had a list of these, so that the dialogue wouldn't be too monotonous. And very often that was triggered by, by a keyword, a modifier saying, I want a cheap laptop, I want something inexpensive, I want a reasonably priced ThinkPad or something like that. So this comes from a system we built for IBM in the UK that was assisting ThinkPad sales when IBM was still selling laptops. So the rules that guided the dialogue were also described in XML, and actually we created a whole description language for dialogue and proposed it at some point as a standard. So a business rule consists of a list of concepts together with some metadata about the target product of service. Okay, so here we have, a collection. So we have a collection of attributes. Yes, so this defines the concept. So it's a notebook, it's a high-tech notebook, and it's a fast. Okay, so essentially a collection of attributes, and we want to connect this collection of attributes with certain action. Okay, in this case, okay, we are connecting it with this specific product. So if we have this collection of attributes and we are relatively certain that that's what the user wants, then this might be the machine that we are proposing, and that may be the specific line that we use in the advertising. The funny thing was that we could propose the machine, but how, the expression of, of the properties of machine had to be approved by IBM marketing, because of course, we were trying to sell IBM products. So a couple of comments about using dialogue-based systems. So first of all, we did extensive testing about effectiveness of dialogues. So we tested both the number of clicks to complete tasks, so for the web-based dialogue. We tested for other dialogues, user satisfaction and also the average time to complete the tasks. So what you see here is a comparison of this happy face dialogue that the diagram of you see here with the regular menu driven, and obviously we see a much faster execution of a transaction, okay, both in terms of the number of clicks and in the, when it comes to time. We also saw higher user satisfaction, and the funny thing was that for spoken dialogue, once the performance of the dialogue manager was about 85–87%, people stopped noticing errors. So they believed that that the system performed flawlessly, even though from the transcripts of the system we knew that that the system misrecognized many of the words or phrases spoken by the user. But since the correction sounded, asking for correction was relatively natural, people didn't mind it. Now, we are now in 2012, okay? Apple introduced, I believe last year, Siri, which is a personal assistant, which allows you to do things like this. You can speak to your cell phone to say, on September 29th, remind me that it's my dad's birthday, and it's gonna put a reminder in your calendar. Some people like it, some people like it less. My daughter owns an Apple phone, so we actually tried it several times. And it works reasonably well with reminders. It doesn't work that well, at least when she speaks or I speak, when we asked about weather prognosis for our town. We didn't try it with, stock market and a couple of other things. But in general, it adapts to you. It is gonna get better. It has, limited number of functions, but these are useful functions. So many people like it. All right. It is aware of your personal context. So you can say, call my wife or send a reminder to my daughter. And if this is somewhere in the database, it will perform the right action. What's also interesting about this model is that many of these functions are not provided by Apple. So there are business partners like Wolfram Alpha that provide the actual service, and the only thing that happens is that Siri parses the sentence and then writes to the API of this particular application. Sometimes these short command-like dialogues are funny. Okay, so here is an example from a website called sirifunny.com. You can find many more funny examples there. So you have, the command, set the alarm for 6 a.m. tomorrow, and Siri somehow provide the answer, I set an alarm for 6 a.m., don't wake me up. All right, I don't know if it's intentional or it is, some mistake in the language model, but it's definitely funny. What is the meaning of life? Obviously, that's beyond the scope of the applications mentioned there. So the good news is that the team has some sense of humor, and they generate, a collection of answers such as this, like all evidence to date suggests it's chocolate. Some other people might get number 42 as the answer, but of course, the system is limited to the particular dozen tasks that it can do, and it does relatively well. So what is the progress that has been made between 99 and 2012? Speech recognition improved quite a bit, but it's definitely still imperfect. We don't know how to do speech recognition reliably as a field, as a computer science field. We are getting recognition rates which are on average in 95–97%. But the problem with speech recognition is that it breaks when something new or something with important information which doesn't exactly conform to the language model when such information appears. So that is exactly the most annoying feature of general speech recognition and machine transcription or machine dictation. That it's not that you have that you get the errors, but you get the errors where the errors really matter. Nevertheless, speech reco is better. Obviously, it can handle a larger vocabulary. We have a dozen of applications instead of one. And then there are some of these, funny replies to general questions. So the vocabulary is larger. The parsers seem to be performing reasonably well. So we have a larger coverage parsing, but I have no idea how Siri parser would compare to the English slot grammar parser that we use in Jeopardy. Now, what's nice about it as an application that it's coherent. Okay, we have multiple little applications all around the same theme, okay, sort of doing assistance with, performing assistance with simple tasks. As a business model, execution delegated to partners API, so the Siri team can focus on improving the interface, improving the speech reco, improving the parsing. I think it's a good business model. Moreover, since there are many users, presumably gathering more data will improve the system's performance. So I think this is one of the applications that we will be hearing about in the coming years, and it will become better, and maybe somebody will create, you know, some breakthrough where we will get to more natural sounding dialogues in more complex domain. So notice though that these are all good things. However, we are still choosing from the small number of options, and we do not have any general purpose natural language processing or dialogue engine. So I would like to speak about some research that is being done, you know, to improve the dialogue, to account for some of the phenomena that have not been accounted for either by, you know, our team in '99 or by Siri. So I use the next couple of slides from a presentation by Johanna Moore, who is a leading researcher on dialogue at the University of Edinburgh. And essentially what she does is she looks at what it is that can be done to improve a dialogue when there are many options, when the situation is more complex, and the user would benefit from, you know, from some changes in the way systems operate. So here we have a situation when somebody is trying to book a trip, yes, and the system says, I found 9 round trips from Hartford to Orlando, and then provides some additional information, and then ends with, please say next option of flight details or I'll take it, all right? So what it means is basically, here's the first option. If you don't like it, ask for the next option. Or if you want more details, ask for the details, or if you think that this is good for you, then take it. Now, 9 is not a big number, yes? So in principle, you could go through it, through all the 9 possibilities, but it would be very tedious. I had a similar experience trying to book a flight to Poland. I went to the website, and it generated over 100 different combinations of, you know, of me getting from New York to Warsaw on a particular day. There was no summary, so the only options you had, you know, you can order by, you know, departing hour or order by price. Neither of these was something that, you know, that was, yeah, I mean, either of these was something of importance, but I would like to have some kind of, you know, a different summary. And presumably the user here would like to have a, you know, some kind of a summary of these options, all right? So user can say next option and get the next, you know, list of details, and then next option and do it 9 times, and then forget what it is that he or she really liked. So what is the issue? Well, there is no comparison. The user has to remember the trade-offs. But if we could solve some of this problem, there would be a large payoff in terms of, you know, how these kind of dialogues are performed. So what researchers are doing in this space is looking at the finer structure of the dialogue, not just, you know, 1 turn, 2nd turn, 3rd turn, but look at dialogue history, at the domain model, at, you know, what it is that user really want. They try to plan the discourse. So in other words, be able to ask questions in a specific order that can be changed depending on, how the dialogue progresses. In addition, linguistic knowledge can be used to provide some capabilities for summarization and make sure that the sentences are not too complex, that they give exactly what the user wants in agreement with the Gricean maxims that we covered 30 minutes ago. So anyway, the point of this slide is that you can do better than just looking at terms and looking at the parameters that you have to fill with a little bit more attention to how people think and how natural language operates. All right, so if we have a user wanting to travel from Edinburgh to Brussels, arriving by 5 p.m., depending on who the user is, we can have, different dialogues. We're going to see a different one in a second. But what you see here is essentially this, okay? There is some kind of a summary. There is a direct flight with a good price, okay? It arrives at 4:10. This is relevant because, we have here by 5 p.m. Price is always relevant to people unless we know otherwise. But it's not the cheapest, okay? The cheapest flight is on Ryanair, but it arrives at 2 p.m. and the price is £50. But it is not a direct flight. So we know something about typical user preferences, that if you have a cheap flight that goes direct, it's better than a cheap flight that has a stop. Now, if we know that the user is a businessman with more money, the system can generate a different answer. You can fly business class on British Air. Business class wasn't mentioned here, but you need to connect in London, so this is an important part. People don't like connections, so this has to be given. And then the other flight, direct flight on BMI, is given as a second option, again with a proviso, with that there is no availability in business class. So this is a much more natural dialogue, which suggests that that we can improve whatever we are doing in this space. So we have here identification and contrast. Okay, so important information is provided and contrast is given. There is a question, certain stuff is implicit about, for instance, the preferences of the users. And what else? I guess that's basically what we want to say about this slide. Here's another example when perhaps this could be even more important. All right. What restaurants are around here could be a question. The system can say, I found 1,000 restaurants. Most are located in Boston and Cambridge. There are 32 choices for cuisine. Okay, so we do have some summarization here, and it volunteers. Yeah, I mean, if you care about the price, I can tell you about the price. So this is a relatively useful summary in a difficult situation where there are too many choices. So the user says, tell me about the ones in Boston. We have still a large number of restaurants in Boston, but there are now 29 choices for the cuisine. So, well, the user wants perhaps something in Boston, and now the choice is seafood. We narrowed the choice to 19. And again, there is a summary of where they can be found to guide the user further. So the user says in the South End, and now we have only 3, which is a much more reasonable collection to choose from. Okay, so in a few turns, yes, so we have here 1, 2, 3, 4 turns, we managed to get from 1,000 of possibilities to 3 possibilities with intelligent interaction and a little bit of dialogue planning. So the dialogue has structure. People have certain expectations about dialogue, and similarly, text has structure. Okay, we are still not using much of the textual structural information that if such information goes beyond the sentence. Okay, so here are some of the rhetorical relations that linguists are discussing. Okay, where you can have something like a thesis and antithesis. You can have a background information, affirmation of the situation, elaboration. There is some purpose often stated, and then there could be a restatement just to, for a confirmation or for adding a detail. Yes, text is often summarized. All of this could be identified in the text, but we do not have good programs that would perform this kind of identification automatically. So here we have a piece of text basically about flowers. Well, there is a title, Bouquets in Basket with living flowers, and then there is a bunch of descriptions. So this is presumably from some Christian Science Monitor article. Now, I'm not going to go through all these sentences. I just want to point out that what can happen and what we would like to do automatically, but as far as I know, we have no such software, is to be able to divide text into this, semantically or rhetorically significant pieces like preparation, background, purpose, elaboration, and so on and so forth. Because, again, people use these kind of relations when they try to understand the text. It most likely will have some bearing on getting appropriate relations from the text and extracting knowledge from the text. But how to do it seems to be still an open problem. And another open problem is common sense. Okay, we recognize certain meanings without any effort. However, for a machine to derive to derive at a correct meaning of simple noun phrases is not necessarily trivial. So, for instance, water bird is a bird who lives near water, but say a marble cake, which is again noun modification, is the cake that looks like marble. So a water bird is not a bird that looks like a water, yes? A soda can is a can containing soda, all right? So, which is yet different relations. So there is no uniformity of these relations between, the modifying noun and the head noun here. Now, rock candy is candy which is very hard, yes, and then eye candy is not even candy, yes. This is, some pretty face or pretty picture to look at, and so on and so forth. So we have bank card, which is a card issued by a bank, but a credit card, which is a card used to make purchases on credit. So here you do purchases on credit, but here okay, you don't do necessarily purchases on a bank. So we have a toy dog, which is a small dog, or a toy shaped like a dog, and a dog toy, which is a toy which is played by a dog. So the modification order matters. So that was, simple, just trying to understand syntactically simple noun phrases. Here we have a situation where you really need to have a lot of common sense knowledge to understand the reference. Okay, so the city councilman refused the demonstrators a permit because they feared violence. Okay, so that would be sentence number 1, and the other sentence would be the city councilman refused the demonstrator a permit because they advocated violence. Okay, so the question is, who feared violence and who advocated the violence? So in one case, the referent of they is the councilman and the other is the demonstrator. Similarly, with the second sentence, the trophy doesn't fit into the brown suitcase because it's too small. Okay, so in this case, it refers to the suitcase, but if you substitute a different adjective, which would be large, yes, the trophy doesn't fit into the brown suitcase because it's too large, suddenly the referent of it is the trophy. People know it, but we do not have a reliable way of giving machine the same kind of knowledge. The last question here, the lawyer asked the witness a question, but he was reluctant to answer it. All right, so obviously here the witness is the referent of he. Now, if we replace answer by repeat, so the lawyer asked the witness a question, but he was reluctant to repeat it, well, most likely the referent is the lawyer. So as I said, we don't know how to give machines common sense knowledge. So there are many examples of such sentences. I give on this slide a few more, and in either of these cases we really need a relatively substantial amount of common sense background knowledge to provide the correct reference for it or they or him. So I forgot to mention, but these kind of sentences are named Winograd schemas for a professor at Stanford who I think was the first one to talk about these problems of reference and common sense. All right, so if we were to summarize the situation, is that we have a rich area of research. We have quite a large collection of existing and emerging applications. We have seen some simple ones, and we spent a lot of time to talk about question answering by Watson, which would be in the more complex category. We have applications that deal only with text, so that also use speech. We have translation applications, we have question answering, And obviously, we have search, which more and more uses natural language processing techniques. So for instance, a few years ago, if you asked a question, Google would simply respond to the document with a document. Currently, if you ask, you know, a simple question like, what is the temperature in New York City, you're gonna actually get the number. Or if you say, you know, at what temperature the water is boiling, you're gonna get 100 degrees centigrade. All right. So search is becoming to be more and more language processing driven. There are many open problems, so we don't know how to deal with meanings in natural language except in a very shallow way. You saw these examples where common sense reasoning is required, and we don't know how to give machines common sense knowledge. We do not have good models for larger chunks of text and for dialogue, and we do not have machines that can deal systematically with, say, various kinds of rhetorical relations within text and perform sort of a natural sounding dialogue. The area is emerging, and for many reasons its importance is gonna grow. In applications, even simple techniques, when applied in a right situation, can give some interesting results. We've seen some of them in first lectures. So we saw a simple application of bigrams to medical diagnosis. We saw some application of word counting to understand the impact of newspaper articles. Some techniques are more complex and require detailed linguistic knowledge. Some of them seem to be very complex, like what we did in Watson. Any of these can be modified and they can be applied selectively. So the moral of the discussion about these techniques is that you have to see what it is that you need for your application. Some applications can function very well with relatively modest parsing capabilities, and some of them can't. NLP is coming to mainstream. We've seen some of the press releases and some of the examples in the first lecture. And it's going to take some time. It took about, 15 years for data mining to enter the mainstream. Now this process is accelerated by something which is called big data, which means that there is a lot of data produced, storage is cheap, so we can actually store all the data well, not all of the data, but a lot of data that's produced. But we have a problem of actually mining this data, and in particular we have a problem of mining text. So big text, that is mining large collections of text, finding some insights there, leveraging it for commercial gain. This is coming. You saw this fragment of a recent article about Watson, where the idea is that that financial companies have hundreds of petabytes of data, and they want to do something with it. A large chunk of that data is text. So dealing with text, knowing something about computational linguistics might be quite useful if you want to work in the technology space. we haven't covered everything. So we talked a little bit about medical diagnosis in the context of Watson, but there is a relatively large area which aims at biomedical text mining. Similarly, we haven't mentioned anything about applying text analytics techniques in the humanities. But of course, you know, Shakespeare, you know, historical work, you know, books are all written in text. Most of them would qualify as humanities. And the only thing that is obvious to everyone is that, well, we can scan all the books and we can, you know, sort of read them online. But of course, much more can be done in this space, and the governments are beginning to realize it. So there are a few initiatives aiming at moving the humanities towards digitization. And finally, within the enterprise, a couple of years ago, I proposed and then ran a project on mining information about intangible assets in the enterprise. So I'm going to say a few words about it after I cover biomedical text mining, digital humanities in 1 or 2 slides each. So with the bio-NLP or biomedical text mining, the idea is that there is a lot of text. In particular, there is a collection of medical text called PubMed, which contains essentially abstracts of all articles that pertain to medicine. It's a huge collection, it's publicly available, and it can be used in many different ways. So for instance, you know, some researchers are working on named entity recognition, so finding names of drugs, chemicals, genes in medical literature, and very often using this PubMed database as a test. Then associations of gene clusters, typically with diseases. So you know what genes you have and how they have been changed, but you don't know if anybody before discovered something similar. So you would like to connect the results of these experiments with the corresponding literature, and this is not necessarily easy to do. A lot of what happens in our body is driven by proteins, interactions with enzymes and other chemicals, and then in turns, genes influencing the production of proteins. So again, these maps of interactions are extremely complex. People are discovering new facts almost every day. But there are no automated methods that would allow you to put all of this information together. So partial methods, for instance, focused on creation of specific drugs for specific diseases, can employ text analytics techniques and natural language processing to create such mappings. Digital humanities. We can digitize information about books, about historical events, but we need to understand text better. So I believe that this is going to be a large source of interesting problems, and there is an opportunity to work with people completely outside of informatics and do something that hasn't been done before. A possible application could be in education, because, for instance, you can build a system that, say, can tutor on a specific topic like history of Poland or the history of ancient Rome. In general, education seems to be changing, but we don't know what the new model is going to be. It seems that things are going towards individualized education, so development of simple modules and then putting these modules together to provide the students with certain amount of knowledge. But we don't have automated tutoring systems. People are working on finding the best modules through a combination of machine learning and natural language processing. I would put my bet that this is going to work only if we are able to combine whatever we learned about games with whatever we can learn about education and tutoring. That is, these applications will work if, like games, they will provide the immediate feedback and a description of progress. Now, what is interesting is that only in New York City, okay, this is the list of, or a recent list of startups that are in this educational space. So the opportunity is large, I would say, and it's probably large in every country. Most of these will probably fail, but some of them seem to, develop sort of some respect, like K Newton, which tries to create this customizable modules from which could be used in schools. And the idea is that students would learn from these customizable modules, and the role of the teacher would be to provide guidance, answer questions, and make sure that other needs of the students are met. So I'm not going to go through this list, obviously, but I think the fact that there is this activity shows that in a couple of years we might be seeing some interesting developments. And finally, in the enterprise, there is plenty that can be done in the enterprise. A few years ago, we created a project on mining intangible assets in the enterprise. So intangibles are assets which do not have explicit monetary value. Okay, so this is essentially an accounting term, and some of them are legal intangibles like patents or trademarks. These do not have the current price, but they are often sold and bought. But there are some other kinds of intangibles like know-how, knowing how to do certain procedure, being able to attract the best employees, so having a good opinion as an employer, and many, many others. So we showed in a project that we ran for about a year that, first of all, that the techniques exist that can combine language processing and data mining, and these techniques can be applied to many classes or many examples of such intangibles. So in this is basically a table which shows the readiness of various kinds of intangibles for mining. Okay, so for instance, it is relatively easy to mine this kind of intangible, this kind of measure, which is profit per professional customers. So if you know what your customer list is, you can actually go to the web, extract information about who these people are, and compute this particular number. The reason people care about it is that apparently this has some predictive value in how well the sales of the company will develop. Ability to attract talented employees. Again, a lot of this information is public, so this could be mined, so you can actually measure this kind of intangibles for yourself and for competitors. Other stuff like plant flexibility, which is somewhere here, or you know, some other stuff like plant infrastructure, which is here, require too much specialized knowledge to be easily mined. But the point of this chart was to show that many of such soft attributes are actually manageable, amenable to text and data mining. What my colleagues did after this project ended was that they used this list of intangibles to build a system that would provide a user some guidance about the value of documents stored on their disk drives, okay? So there was actually, you know, an application of this table that was used in a product. So I want to point some resources at the end. So if you want to learn more about NLP, you of course can start with Wikipedia, which has plenty of articles. I used some of them, some of the diagrams from Wikipedia in this class. It's an excellent source in general. But if you want to go beyond Wikipedia, then aclweb.org has a list, I mean, has all the NLP papers that appeared in the last 20 to 30 years. Okay, they are freely available, so any topic of interest, syntax, semantics, language models and semantics, machine translation, you can find papers there. If you want to experiment with some corpora, this is the place from which you can get many of them. Some of them are free, some of them are not. In other, I mean, for instance, IBM has to be a member and pay a membership fee to get some of the resources from a Linguistic Data Consortium. I listed some of the websites, but of course there are, you know, these are websites of either groups or particular researchers. So I listed the Stanford NLP group, which has, again, a very large list of resources. I used quite a few slides from the site of Dragomir Radev, a colleague of mine at IBM and now professor at the University of Michigan. There is a strong NLP group at the Columbia University in New York City. So this has pointers to the work that's done there, and this includes sort of bio-NLP that I mentioned in the last slides. There is interesting work on dialogue that's being done at the University of Edinburgh in Scotland, in the UK. So Johanna Moore, whose slides I used today, works there. If you want additional pointer, go to Google, type NLP and restrict to site edu, and you're going to have quite a few pointers. So I'm going to end this class with this list, and if you have any questions, I will be happy to answer.